Hello, MM. You're the only one absent today, so that's quite an honor. We were having trouble moving forward without you, but we pushed on. And we studied potential and kinetic energy again in the mass spring system. It's April 1st. And we took a spring mass and we pulled it down to its amplitude position. We held it and released it. And we're just going to do a trace through a couple steps of potential and kinetic energy. We learned that total energy in the system is like it used to be, is anywhere at any point kinetic plus potential. So we've seen that before in other scenarios. And KE is going to be the same. It's 1/2 mv squared. And PE, however, is different for the mass spring system. And it's 1/2 kx squared, where k is the spring constant and x is the distance from equilibrium. So, and these are all measured in joules. When I pulled the mass and on the spring downwards, I added energy to the system. I held it and then released it. Right when I released it, there's no velocity for an instant. So that means there's no kinetic energy, because kinetic energy was motion, all potential. So at this point, kinetic energy is 0 and potential energy is at a max. And that should bear up with this formula because x is at amplitude. So it's the furthest away that's going to be, so it's going to be the biggest number. 1/2 k spring constant x squared. X is at the max at amplitude. Then as it goes up, we remember velocity increase, so does kinetic energy. So I'll say kinetic energy plus went up, and potential energy, because the x, the distance from where it is to equilibrium, is smaller, potential energy went down. And here, right at equilibrium, the velocity, you'll remember, is at the max, so is kinetic energy. So kinetic energy maxes out at equilibrium, but potential energy is the restoring force that's bringing it up. The x value is 0 because it's at the equilibrium, so there's no potential energy right there. So potential energy zeroes out. And this sort of thing kind of repeats itself. But those are the main points of interest. So if I was going to graph this idea, let's move over here and make a fine graph. Let's see if you can write this as I do. I'm going to take a axis here, the vertical axis, and I'm going to plot my energy amounts on it in joules. And along the horizontal axis, I am going to do the distance, we call it displacement, from equilibrium. So that'll probably be in, we'll say in centimeters for our purposes here. So here's what we're going to do. We're going to put the distance from equilibrium, we're going to put 0 in the middle. So that means at this point on our graph, we are at equilibrium. But let's say we pull the spring down, we are far away from equilibrium. So I'm going to say this is 5 centimeters, 4, 3, 2, 1 centimeters away from equilibrium. Then it'll pass equilibrium and go far from it again. 1, 2, 3, 4, 5. So an unusual way to number the x-axis, but it represents what's happening. It's 5 away from equilibrium right when I release it. 4, 3, 2, 1 at equilibrium. Then it goes past it. 1, 2, 3, 4, 5. So alright, so, and energy, we'll say this is the max, and this will be no energy. So let's plot potential energy first. So potential energy, when we are at, let's say, at amplitude right here, what's happening to potential energy at amplitude? At the amplitude, you'll see the potential energy was at a max. And then at the equilibrium, it went down to 0. So potential energy is going to start up here at a max and go down at equilibrium to 0 and then back up to a max. And because this is a quadratic relationship, we have a squared. It's not going to be a straight line, so we're just going to make a curved line like that. And that's PE. That's potential energy. Now kinetic energy is going to work differently because it started at 0 and then went to a max. So when we're at amplitude, it's down here at 0, and at equilibrium it was at a max and then it went here. So KE, I'll dot it so it looks different from the reason I'm videotaping this at home is I forgot my camera today, so you get an old boring home video. Alright, so write down this graph in your notes and we'll go from there. These ideas will help us, and these formulas will help us with our problems, and we only had like a 30-minute class, basically being half a day, so I think we got through one example. So the first example, we had a mass spring system and we pulled it down, and when we pulled it down 14.1 centimeters with our pull, and the mass then looked like this. We'll say it was 11.2 kilograms, and the pull was added 35 joules of energy to the system. So this is equilibrium up there. So the question was find K. So we had to look up here and pick a formula, and the only one with K in it was right there. So we grabbed it, and we said PE equals 1/2 KX squared. And we're looking, the biggest step is we're looking at this at amplitude, and at that point all of the energy, you'll recall, is right here. There's no kinetic, it's all potential. So all of the energy added to the system, all 35 joules, was potential at that point. So we are allowed, in this case, to put 35 for potential energy. 1/2 K is what we're looking for, and we are at amplitude where we pulled it down the max, and that was 0.141 meters. So that's squared by the formula. So when we plugged that in and solved for K, we got K equals 3,500 newtons per meter. And that's all we had time for, because we also asked, we said find K, and we also said, I wrote kind K, find K, it is late, find K, also find the maximum speed. So to do that part, the equation that has to do with maximum speed, the only one is velocity there. So we're going to grab the KE. So we're going to take KE equals 1/2 mv squared. And it turns out that kinetic energy, it's going to have the maximum speed here where kinetic energy is at a max. So those 35 joules that we use to pull it down will have all been lost, all that potential energy be converted to kinetic. So at the max here, where it's the max speed, it's 35 joules again. So it's a little tricky, but we can put that 35 in at the equilibrium from KE, and we can put it in at amplitude for PE, and that equals 1/2. The mass was 11.2 and velocity squared. So when we solved that, we got 2.5 meters per second. All right, so we started the next one, but we didn't get very far, so I'm just going to leave you there on that. The math that we did was on logarithms, and we had a video on Thursday night, and the homework is on page 236, and it was numbers 1 to 16 odd. We didn't have very long. And number 27 to 30 all, and number 79 to 86 all. So let me show you those problems, and the more you can do before you come back, the better. And I hope you're okay. So we did 1 through 16, and then we did 27 through 30. That's showing up kind of a weird light. And we did 79 to 86. Alright. Alright, I hope this is helpful and that you're doing alright. Have a great weekend and see you on Monday. Bye.